Good evening, good afternoon, hello. We're going to talk about what we call two-dimensional interactions. So we've talked about two body interactions so far, two object interactions, but only in the context of them happening in one dimension. So, objects can only move left or right or east or west or north or south. Now we're going to say that at the same time, one object might be moving in one dimension while another object moves in another direction or dimension. All right. And so, in this case, we have two objects moving perpendicular to each other. That doesn't have to be the case, but that's the simpler of the two-dimensional cases. And let's look at a case where this is a hit and stick, or what we call an inelastic. All right, in means not. Elastic means bouncy. So these things hit, and there's no bouncy. All right, they hit and stick together. So, well, if I say that these are their momenta, initially, well, what we can do right off the bat is sort of say that the net initial momentum is the sum of those two momenta, really the sum of those two vectors. So it's this plus this. Here's P1 initial. Here's P2 initial. Here's the net initial momentum. Right? And each of these initial momenta you could find if you needed to. Well, if you were given enough information, right? M1 V1 initial. M2 V2 initial. So if these things hit and stick together, groupy group group, then clone. They hit and stick together. Right? They're stuck together, and now, well, what are they going to do? Well, we already know the answer. Because during any and every two-body interaction, momentum is a conserved quantity. So the system, no matter when you look at it, has the same amount of total momentum. Well, and here is that amount of momentum. So that means that the system has still that same amount of momentum. Afterward. I draw those the same. I didn't do a great job of drawing them exactly the same. That's pretty good. I'm happy with it. Now, if they stick together, what we would say is that the net final momentum is that, right? Oh, and just so we're sure, I know you recognize this is a right triangle, so of course we would say that the net initial momentum is the sum of, well, sorry, yeah. We use Pythagorean theorem to find the actual value, the magnitude of that initial momentum. We could do some trigonometry to find the value of that angle. So that is the same exact direction that the system moves in at the end. All right, and that is the same exact momentum that the system has in the end. We want to find the speed of the system in the end. Well, we do this. Make sense? Okay? Let's look at this case where these objects collide and bounce off of each other, or we call this an elastic collision. All right. right, now what I'd sort of have to tell you, again, we could say this is the first one's initial momentum. This is the second one's initial momentum. Now, there's a lot of things that could happen in the end. It really depends on a couple of conditions that we won't really talk about just yet. But let's say that the following happened. Let's say that in the end, number one ends up, I don't know, with that momentum. Okay? The question is, what's the second one going to do? Well, we still have to use the fact that the net initial momentum is the same as the net final. But here's what this actually means. We can actually turn this into two statements. We can say that the net initial momentum in the horizontal direction is equal to the net final in the horizontal, and that the net initial in the y direction is the same as the net final in the y direction. So we can look at components of momentum, because in the beginning, look, the system has this much momentum horizontally. And so it better have that same exact amount horizontally later. Well, how much do we have so far? We have this much. So here's P1 final X. And let's say this is, I don't know, 10 kilogram meters per second. Just made that up completely. Well, if this is, say, I don't know, looks like maybe 8 kilogram meters per second. I think 8. Yeah, I'd say 8 is reasonable, right? Well, where'd the other 2 go? They went right here. So that is P2 final X, which has to be 2. Make sense? And P1 final has that vertical component, which, it actually looks bigger than that. So, move that back. Let's call this, I don't know, let's say this was 4. All right, this is 10, that might be 4, right, reasonably? Well, and this is going to be 5. Right, and why is it 5? It's a little bit bigger, right? Sure, 5. So what does this number 2 have? Well, we had 4 units downward. This one has 5 units downwards. This one must have 1 unit. 2 final y, 1 kilogram meter per second. So the 5 downward and the 1 upward equal the 4 downward, right? And so this thing, number 2, if number 1 ends up doing what we just arbitrarily picked that it does, have a momentum that looks like that, then number 2 must, therefore, have a momentum that looks like that in order to conserve momentum. Now, I hear a lot of you saying, what do you mean? You're telling me 2 is going to start like this and end up bouncing back upward? I mean, that's what you get for making up a crazy example like this. But, maybe if 1 is more massive than 2, we saw how when objects collide with objects that are more massive, that are stationary, that they bounce back off and go the other way. And as far as the y direction is concerned, number 1 is sort of stationary. It's moving this way, but doesn't have any vertical momentum. So, it is sort of like that case where an object collides with a more massive stationary object. This one will start moving that way, and this one has to bounce back that way. All right? So, Again, I made this example up completely. Could it happen? Maybe. Okay? But what we're trying to show is that you have to sometimes be able to look at momentum in each direction and make sure that you're conserving momentum in each direction, each of two perpendicular directions. You got me? Now, the other thing that would have to happen, and I don't know if this is true, but this is maybe more than we have to talk about. If we took this original 10 and this original 4, here's our total initial momentum, right? Well, in the end, we'd have to take, look at this is crazy, P1 final and P2 final, that's this vector right here. So I'm going to add that one tip to tail with this one, not necessarily some right triangle thing, but here's our, so that's P2 final. Here's our total final momentum. Holy cow, look at this. It looks pretty much like this. It looks just like that, doesn't it? Yeah, pretty much. If I did all my drawings just right, it's the same exact vector. Right? We add up all the initials. That's P1 initial. That's P2 initial. We add up all the finals, P1 final, P2 final, and we have to get, if we've drawn our things just right, we have to get the exact same vector sum. Okay? Now, perfectly elastic cases. Perfectly elastic means something. It means kinetic energy is conserved. All right? And it's hard to do. It's an ideal sort of situation in which objects actually can't touch each other. If they touch each other, well, there's typically some deformation of each object. There is, in most cases, some sound that's produced, right? You hear that contact happen, and things will heat up a little bit. So this is, again, another one of those sort of idealized situations, but it's a nice model of, you shoot a proton at another proton, and they'll get close together, but they're not going to push into each or touch each other because there's an electrostatic force that gets real big, and so they can make each other sort of veer off in different directions. Whoa, neat. Without ever coming in contact. So those are cases where we can really sort of, what's the word? The word is assume. It's not assume. It's, I don't know. It's a case in which we can model in a perfectly elastic collision. But let's assume that one looks like this. And we're going to take the case of two billiard balls. Definitely not perfectly elastic, but pretty close. You certainly hear two billiard balls hit each other. But let's just say that there's a perfectly elastic collision. Forget about that it's two billiard balls, but let's look at what happens. Here's P1 initial. All right. Here's P2 final. And the question is, what's P1 final have to look like? All right. Well, one thing is momentum, the vector, has to be conserved. All right. And so that says that from that we could actually say that, well, if this is the initial momentum, it's got to be the same as the total final momentum. So this is also the final momentum. And here's one of the final momentums. And so the other final momentum has to look, hey, you jerk. The other final momentum, come on, over there, has to look like this. How do I make that stop doing there? It has to look like this. Right? So here's P2 final, here's P1 final. Now, since kinetic energy is conserved, check this out. Momentum, mv, right? Kinetic energy, 1/2 mv squared. Now, we're going to say that this has some kinetic energy of 1 in the beginning. This has some kinetic energy 2 final, and this is going to have some kinetic energy 1 final, and those have to add up. KE1 initial equals KE1 final plus KE2 final, right? Now notice, if we were to take momentum and square it, we get m squared v squared. Right, well, here's something with v squared. Well, if we were to divide it by 2, okay, there's a divided by 2, and then divide it by m, and divide it by m. Now look, on the right side we have mv squared over 2. That's kinetic energy. So apparently kinetic energy is the same as momentum squared over 2m. You follow that? P squared over 2m, I'll do it again. P squared is m squared v squared over 2m. Well, that's the same as, oh yeah, 1/2 mv squared, right? So we can express kinetic energy of any object as P1 initial squared over 2m equals P1 final squared over 2m plus P2 final squared over 2m. The reason I mentioned billiards in the beginning is if the masses are the same, look what happens. Divide everything, well, multiply everything by 2, multiply everything by m, and what we end up with is this. Right? So two conditions have to be met. Here's one. The other is what we just said here, that P final is P1 final plus P2 final. So the vectors have to add up. That's just a conservation of momentum statement. And here, the sum of the squares has to equal the square of that, which only works if this is a right angle. And the reason I like to talk about this is if you're a billiards player, you got a table that looks like this, right? You got you got a ball, a target ball or an object ball, I think they call it, right here, and then here's the cue over here. And sometimes what you say is, well, you know, if I try to put the 8 ball in this corner, how do I know if I'm going to scratch or not? Well, what you can do in a lot of cases, if you're not a super duper pool player where you can put spin on the ball and, you know, blah, blah, blah. If you just do a plain old collision here, and assuming that it's pretty much perfectly elastic, even though it isn't because it makes some sound when the 2 balls hit, what you have to do is sort of say, well, we know this ball is going to, if we hit the shot right, it's going to go at that pocket, right? We want to put the 8 ball in there. So what you have to do is say, well, what's perpendicular to that? Because if this thing is really a nice, perfectly elastic collision, then we know that this ball is going to end up going perpendicular to that one. And if perpendicular to that leads you towards a pocket, there's a pretty good chance you're going to scratch. All right? So bear that in mind next time you're hustling people for money out in the pool tables. All right? Check your perpendiculars, people. I can't stress that enough. Yeah. So, a couple big things. One, momentum's a vector, and so it can be conserved in 2 directions. All right? In a case like this, we can look at total initial momentum as the sum of two momentum vectors. All right? And then we can say, all right, if these two things stick together, then their final momentum is the same as the initial momentum, and, well, we can figure out things like what direction the system will move at. It's the same as the direction that the initial momentum vector points at. All right, we can figure out how fast the combined system will move. It'll move that fast. If things collide and don't stick, don't stick together, well, we can look at the components of momentum in each direction and make sure that we conserve momentum in each direction. The total initial momentum in this direction has to be the same as the total final. The total initial momentum in this direction has to be the same as the total final. So sometimes you'll have to do two different conservation statements, one in a horizontal direction, one in a vertical. Okay? And big deal here, if you see a reference to something being perfectly elastic, or if a question asks you, is this a perfectly elastic collision? What they're asking for is kinetic energy conserved? In a perfectly elastic collision, kinetic energy is conserved. We did all this stuff about a special case where masses are equal. Right? In that case, the two objects have to end up moving at right angles to each other. And therefore, if and when you're playing pool, be careful. All right? But in general, the important part about this slide really is this connection. We can start to look at how much energy changes, or if energy changes, during two object interactions. Kinetic energy will change if a interaction is not perfectly elastic. So when you have a case like this, objects collide and stick together, kinetic energy not conserved. All right, momentum definitely conserved, always. Every kind of two-object interaction, momentum will be conserved. But kinetic energy, sometimes yes, sometimes no. In an inelastic, never conserved. Kinetic energy is never conserved in an inelastic collision. We can prove that really easily. You want to see how? Let's just make sure we do. Let's do this case. M, V. It's a same mass object. In the end, sticks together. We agree that the system now moves at a speed v over 2. I hope. Can we agree on that? We should be able to. All right. If we look at, so we did this. By saying that, right? Check. It works. This is just mv equals 2m v over 2. Yep, works. mv equals mv. Momentum always conserved. What about kinetic energy? Well, if we say here, the kinetic energy, 1/2 mv squared. In the end, so in the end, it's 1/2 of now 2m, and v is v over 2 and squared. Well, let's see. That can go with this. So that's m v squared over 4. Or that's in the beginning. In the end, so not the same, right? We lost that much kinetic energy. We went from 1/2 mv squared down to 1/4. Means we lost 1/4. So you can compare initial and final values of kinetic energy and see how much has been lost. But here's a proof that in an inelastic collision, kinetic energy cannot be conserved. Okay? So I kind of got into a couple things. I wanted to make sure we talk about two-dimensional stuff, but also get into this idea that we can also look at how much kinetic energy a system has before and after a two-body interaction. Why do we not talk about potential energy? Well, because we would really not talk about, during a collision, typically changes in height, right? Or stuff with springs. Okay? Okay, folks.